And we're now recording. So we're getting near the end. Welcome to May. So once it hits May, you know we're almost done. I did mess up on one of the problems last time. What else is new, right? I think it was question number 2. So I sent you a little Canvas announcement on that. I switched around a U and a V, I think. Okay, 16.7, 16.8, 16.9, test 5, review for the final, and then the final. Okay, for the final exam, it'll be problems that are very similar to the previous exams. So you might say, how do I study for the final exam? Just go off the previous exams. And as far as cheat sheet is concerned, just bring all the previous cheat sheets. No need to remake them all over again. Just bring in the cheat sheet from the first test and a cheat sheet from the second test and a cheat sheet from the third test and a fourth test, fifth test. Just put them all together for the final exam. Okay, and we'll just review for the final on Tuesday, the 18th. Okay, so a possible scenario would be, let's say, I just pick 3 questions from every test, and I'll just say, okay, I like these 3 questions from the first test, and I like these 3 questions from the second test, and I like these 3 questions from the third test, and so on. And that's how I'll construct the final exam. That doesn't mean I have to ask the very same question, but I might, or I just might modify it a little bit, and that'll be the final exam. Okay. All right, so 1 section a day, although today there's a lot of formulas, 16.7. 16.8 has basically just 1 formula to put in your cheat sheet. I'll at least show that to you. And 16.9 is basically just 1 formula. So you can put that on your formula sheet. So at least you've got all the formulas out of the way, and I'll show that to you. And besides, my normal procedure is, again, if I can sneak in a little bit of the next section just to get ahead in case I fall behind or something goes wrong, then I'll do so. Okay. So that's what's going to happen. And 16.7, more problems to throw out. Throw out the last one, problem 31. Okay. And these problems are actually very good, but they're really, really long. It's actually hard to come up with good problems which are not super long and that you can finish in a quote unquote reasonable amount of time. Okay. So that's what we're up against. Okay, so I'll try to do as many of these as possible. Your quiz next time will be based on a problem that I do today, very similar to it. And it's a kind of problem where I'm not sure I'll ask you the whole thing on an exam, but for a quiz where you can talk to each other and help each other out. It's not really hard, it's just very long, okay, and tedious. Okay. All right, so we'll get started with 16.7 then. Okay, so any quick general questions? Let me check the chat. Or anybody want to unmute yourself? Any questions about where we're headed? So we'll be done very soon. Almost done. Okay, so hearing nothing, let's get started with 16.7. And by the way, for some of these, I was going to show you at least a little bit of why I threw some of them out, which means you don't have to take notes, but I just show you, what was involved. Then I got to a certain point and I said, forget it, it's too long. I'm not going to torture you with it. It's torture for me. So if it's torture for me, it's probably torture for you too. Okay, so I may just actually show it to you, and then I made a little comment, it's too long, so forget it. Okay. All right, so what do we need for 16.7? The topic is surface integrals. So you're integrating across a surface. Okay, so equation 2. Here on page 1123. Double integral across a surface S f of x, y, z ds is f of r of u of e, magnitude of ru cross rv dA. Okay, so that's when you have function represented parametrically in terms of 2 variables u and v. Okay, in the special case where you have z as a function of x and y, you have this, number 4. Put that in your cheat sheet. F of x, y, z, f of x, y, g of x, y. And then square root of partial z with respect to x squared plus partial z with respect to y squared plus 1 dA. And you might recall this is a formula for ds. So if we're integrating only that, if you didn't have all this stuff, you're getting surface area. But in general now, we have a function across it. And again, I should say, or the equivalent. So this is the equivalent. Suppose you have y as a function of x and z, then likewise partial of y with respect to x squared plus partial of y with respect to z squared plus 1 dA. I think there's actually one problem that involves something like that. Okay, where you have z as a function of x and y for oriented surfaces. Okay, positive, the n is a normal vector, positive is up, negative is down. If you have z as a function of x and y. If y is a function of x and z, then positive is to the right, because that's the way y is. And if x is a function of y and z, then positive is coming out toward you, because that's the direction of positive x. Okay. And let's see, for closed surface, so we'll have a problem like this on 1128. You have a closed surface, because you can't really say which is positive because you're going all directions, like for sphere or cube, then positive is considered outward and negative is inward. Okay. It's very logical because inward is bounded. You can't go infinitely far, but you can go infinitely far out. So we decided, okay, if we're going to have infinitely big numbers, we want that to be positive, and then a small negative, like -10 or -20. If we went the other way, then negative could go out to infinity, but a positive would be a small number. Okay. All right, then 1129, you want equation 8. Integral of f dot ds, that's sometimes called the flux of f across s, across the surface. Double integral of f dot n ds. Now you would do that if you have a very nice normal vector. Okay. Now, you may not have a nice normal vector in pictures like this, figure 1, where it keeps changing. Imagine the normal vector keeps changing as I go along. But certain instances, and I'll show you when, it's not that bad. It's also called the flux of F across S. Okay, so flux. So if you have a closed surface, the flux of any field, such as a flow of heat, okay, like in a building, okay, what's the rate of change of heat across all the surfaces? Or it could be, electrons. Okay, electrons flowing in and out of a substance. It could be the flow of water, okay, or air, or anything. Okay, very logical for an organism like you and me and any living substance. There's an exchange, right, within the surface, your surface, or the surface of an animal, or the surface of a plant. There's exchange of water, there's exchange of air or gases going on, exchange of heat. So all of that is going on. So the flux of F across S, again, positive is considered outward. So you and I, when we get too hot, then we sweat and heat comes out, right? So we have heat coming out, or water can come out, or we get too thirsty, so we have to drink water. Water comes into the system, right? Okay, and one more here. Integral of F dot ds, F dot RU cross RV dA is another possible formula. Okay. And another one, number 10. Double integral of F dot ds. Okay. So you have z as a function of x and y. Okay. They put the partial of g with respect to x, partial of g with respect to y. Might as well pretend it's a partial of z with respect to x. It's unnecessarily complicated, in my opinion. Okay, double integral on s. S is a surface in space. D is in a plane, the xy plane, or the xz plane, or the yz plane, or the uv plane. Okay, this is the PQR defined by F, negative P, z sub x minus q, z sub y plus r dA. And I think we're ready. Okay. So here we go. Okay, 16.7, number 1. So here's a good example of flux across a surface. Let S be the surface of the box enclosed by the planes x equals plus or minus 1, y equals plus or minus 1, z equals plus or minus 1. So you get a cube, right? So imagine a box, x goes from -1 to 1, y goes from -1 to 1, z goes from -1 to 1. So you have a box. 2 by 2 by 2, right? -1 to 1, x, y, and z. Approximate the double integral of cosine x plus 2y plus 3z ds by using a Riemann sum as in definition 1, taking the patches S sub ij to be the squares of the faces of the box S and the points to be the centers of the squares. Okay, so the representative point that you're picking is the center of each square. Okay. So here we go. So here we go. X equals -1 to 1, y equals -1 to 1, z equals -1 to 1. Okay. Each of the 6 squares is 2 by 2. So dA for each little piece, each square is 2 times 2 or 4. All right, so you have a front, a back, left, right, up, top, and bottom. Okay. So they said take the center of each of the 6 pieces. So the center of the front face is 1, 0, 0. Right? You're going from -1 to 1 for x, y, and z. So the front face, x is 1, but the center would be y is 0, z is 0, right? The center of the back is -1, 0, 0. The left would be 0, -1, 0, the center. The right is 0, 1, 0. The top center point is 0, 0, 1, and the bottom is 0, 0, -1. Okay, well, should I try this? It might clutter up the picture, but I'll try it. So the front and the back are sort of like that. Okay, that's supposed to be the front. That one's the back. Here's the left, right, top, and bottom. That's supposed to be the center of the front, center of the back, center of the left, center of the right, center of the top, center of the bottom. Okay, so the double integral over the region S of cosine of x plus 2y plus 3z ds is, I add up the function values at all 6 of the faces. The dA in each case is 4, right? The area of the front is 4, 2 by 2. So for the back, left, right, top, and bottom. So factor out the 4. And then the cosine of, for the front, it's 1 plus 0 plus 0, or cosine of 1. The back, I plug in -1, 0, 0. So cosine of -1 plus 0 plus 0. Okay. And then the left and right, if I plug in -1 for y, I have the cosine of -2. For the right side, it's the cosine of 2. I guess I did the right and then the left. And then top and bottom, 0, 0, 1, 0, 0, -1. Plug in 0, 0, 1, that's cosine of 3, and cosine of -3. Okay, so that's the function value at the midpoint of the front, back, right, left, top, and bottom. I plugged in all these guys. So the front, plug in 1, 0, 0, 1, 0, 0, cosine of 1, radian. The back, -1, 0, put in -1, 0, 0, cosine of -1, and so on. Okay, now cosine is an even function. That means cosine of 1 is the same as the cosine of -1. So I actually have 2 cosine 1. Likewise, cosine of 2 and cosine of -2 are the same. So I have 2 cosine 2, 2 cosine 3. I factored out the 2. So I have 8 times cosine 1 plus cosine 2 plus cosine 3. Punch in your calculator, -6.93. So that's the answer to that one. Okay. Now, number 5, it's described parametrically. double integral across the surface of x plus y plus z ds. X is given to be that, y is given to be that, z is given to be that, u is going from 0 to 2, v is going from 0 to 1. Okay. So number 5, evaluate the surface integral. Can't quite get it all there, but it is there. Okay. So to evaluate that surface integral, represented parametrically, I do that. Change x, y, and z to u and v, and then the magnitude of RU cross RV dA. That's your Jacobian, by the way, that magnitude of RU cross RV. So ds is equal to Jacobian dA, magnitude of RU cross RV dA. So first I figure out x plus y plus z. So x is u plus v, x plus y plus z is u plus v plus u minus v plus 1 plus 2u plus v. And if I add them all up, I have u plus 2u, 4u. And v minus v plus v is v and 1. Okay, so my integral is going to be 4u plus 4v plus 1. And then I need a Jacobian. So RU cross RV. So RU, derivative with respect to u. We say we're taking the derivative with respect to u, but we're actually taking 3 derivatives with respect to u, right? That one, and that one. Okay, so R sub u, derivative with respect to u is 1. Derivative of that with respect to u is 1. Derivative of that with respect to u is 2. Then R sub v, derivative with respect to v, 1. Derivative with respect to v, negative 1. Derivative with respect to v, 1. Okay, so it's I times 1 minus a minus 2, which is 3. The opposite of 1 minus 2, which is negative 1. And then the k component is negative 1 minus 1, which is negative 2. So 3, 1, negative 2 is RU cross RV. And then I need its magnitude. So the magnitude is a square root of 9 plus 1 plus 4. 9 plus 1 plus 4, radical 14. That's my Jacobian. Okay, then I'm pretty much home free. So double integral, they told me u goes from 0 to 2, v goes from 0 to 1. It doesn't matter which one you do first, of course, by our rule that we said, right? Fubini's theorem. So I went v goes from 0 to 1, u goes from 0 to 2. Of this is x plus y plus z, x plus y plus z, except I plug in for u and v, right? X plus y plus z times the Jacobian, radical 14, dv du. Okay, so I took out the radical 14, you can take constants out. Integrate with respect to v. So 4uv plus v squared over 2 plus v. V goes from 0 to 1. Plug in 0, you get 0. Plug in 1 for v. 4u plus a half plus 1, which is 3 halves. So I integrate 4u plus 3 halves with respect to u. 2u squared plus 3 halves u from 0 to 2. Plug in 0, you get 0. Plug in 2. 2 times 2 times 2 is 8. Plug in 2, 2 cancels with 2, 3. 11 radical 14 is my answer. Okay. There we go. Okay, 7. Double integral of y ds. Number 7. S is the helicoid. Don't worry about what it looks like. It has something to do with the helix. R of u, v, u cosine v, u sine v, v, u goes from 0 to 1, v goes from 0 to pi. Okay, this is exactly the same thing as if it said x equals blah, 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 y equals blah, 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 z equals blah, blah, blah. So in other words, it's not any different than problem 5. See problem 5 where it says X equals whatever, Y equals whatever, Z equals whatever. It's actually more compact to do it like this. Okay, they give you the position vector R. So if the position vector R is given, this is X, Y, and Z. Okay, same thing. All right, so what's my integral? I'm integrating Y, which is simply U sine V. So when it comes to integrating later, there's Y, U sine V. Okay, X, Y, and Z. So by formula, I need R sub U, the derivative with respect to U. Differentiate that with respect to U. So derivative with respect to U, cosine V. Derivative with respect to U, sine V. Derivative with respect to U, there is no U, that's a V, so 0. R sub phi, derivative with respect to V, negative U sine V, U cosine V, 1. Take the cross product, IJK, cosine V sine V 0, negative U sine V, U cosine V 1. So the I component is sine V minus nothing. The J component is the opposite of cosine V minus nothing. And the K component is U cosine squared V minus a minus U sine squared V. And if you take a look over here, this is the same as U, right? Because you can factor out the U, and you have cosine squared V plus sine squared V, which is 1. All right, so that's sine V, cosine V, U. So what is the magnitude of RU cross RV? Square root of sine squared V plus cosine squared V plus U squared. And sine squared V plus cosine squared V is 1. So radical 1 plus U squared. That's my Jacobian. All right, so I'm ready. So back to the integral. I'm integrating Y, U sine V. That was my Y, wasn't it? The Y coordinate. So U sine V times my Jacobian, radical 1 plus U squared, dV du. V goes from 0 to pi, U goes from 0 to 1. So that was magnitude of RU cross RV. Okay, integrate with respect to V first. Integral of sine is negative cosine from 0 to pi. Still got U radical 1 plus U squared du. Take out the negative, got a lot of negatives. Cosine of pi is negative 1, minus cosine of 0 is 1. So I have negative 2, which is 2. Now I temporarily put it outside, but I realized I have to put it back inside to do my substitution, right? If I were to do well, I can't say U substitution anymore because I've already used up U, so a V substitution. What's the derivative of 1 plus U squared, 2U? So sneak in the 2 back, right? So if I do a V substitution, I'm basically integrating V to the half. So there it is. 1 plus U squared to the 3 halves divided by 3 halves means times 2/3 from 0 to 1. And then I'm pretty much home free. 2/3. Plug in 1, you get 2 to the 3 halves. Plug in 0, you get 1. And you recall raising something to the 3 halves like this, 2 to the 3 halves is 2 radical 2. So final answer, 2/3 of 2 radical 2 minus 1. And there we go. Okay, so I'm done with that page except for part of 13, which I messed up, and I think I decided not to have you do it anyway. Was that right? Yeah, skip 13 because it was going to be too long. All right, I'm done with this paper, so let me do my focus thing again. And in the middle. And then the right column. And that's it. And you see the rest of it. Okay. Right, I was just going to show you a little bit of how bad this can get. So 13, so you don't have to pay attention for now. 13, double integral of z squared ds. S is the part of the parabola, x equals y squared plus z squared, given by x between 0 and 1. So you don't have to pay attention. This is not assigned because show you how bad it got. Okay, so x is between 0 and 1. If I plug in 0, I have the origin. If I plug in 1, I have y squared plus z squared, which is a unit circle in y and z. So x is a function of y and z. So x sub y, derivative of x with respect to y is 2y. Derivative with respect to z is 2z. So I'm doing the double integral of z squared z is r sine theta. Okay, think back to the yz plane. That's sort of like xy. So z is r sine theta. So it's r squared sine squared theta z squared times the square root of 1 plus z sub x sub y squared plus x sub z squared, which becomes radical 1 plus 4r squared times r dr d theta. Okay, and you can see this is going to be real bad. You have r cubed and a 1 plus 4r squared. You can do it with a trig substitution, but it's just way too long. So that's the reason why I decided to skip it. All right, so that's what happened over there. Okay, 15. I'll show you that one. Double integral of x ds. S is a surface, y equals x squared plus 4z, x between 0 and 1, z between 0 and 1. So this time we have y as a function of x and z, not our favorite. Okay. One nice thing about 13 is 13 had x as a function of the other two variables. Okay. Instead of our traditional x is a function of z is a function of x and y. 15, we have y as a function of x and z. So we have to keep that in mind. So I'm essentially using this formula. But I have to keep in mind, it's not the partial of z with respect to x and y. It's going to be the partial of y with respect to x and z. In other words, this version. Problem 13, which would have been nice, would have been the third variation where x is a function of y and z. Then this would be partial of x with respect to y, partial of y with respect to z. Okay. This one's not too bad. So I need the partial of y with respect to x, 2x. Partial of y with respect to z, 4. It's y sub x, y sub z. So this is not so bad. So I'm doing a double integral of x square root of 1 plus y sub x squared, 4x squared, plus y sub z squared, 16. This is the Jacobian, dx dz. Okay, and of course that's 4x squared plus 17. So I'll do a u substitution. If u equals 4x squared plus 17, du is 8x dx, right? So I need an 8 inside and a 1/8 outside. Furthermore, these are all constants, 0 to 1, 0 to 1. This equation does not, this integral does not involve z. So just take out the z and multiply it by the length of the interval. The length of the interval is 1, so I don't even have to worry about it. Just forget about the z, just worry about the x. So it becomes u to the half. So u to the 3 halves times 2/3 from 0 to 1. And 2 cancels 8, 4, so 1/12. Plug in 1, 4 plus 17, 21 to the 3/2, minus plug in 0, 17 to the 3/2. Okay, so I'm not sure why this was in red, but final answer 1/12, 21 radical 21 minus 17 radical 17. Okay. $17 was going to come out real long. Okay, so it's so bad. I think I'm only going to show you part of what happened. But so again, just another one of those that I decided to throw out. So make sure that I put that in the homework list. Skip 17, yes. So you don't have to pay attention for 17 if you don't want to, but just give you a feel of how bad it is. Okay, double integral of x squared z plus y squared z ds. S is the hemisphere, x squared plus y squared plus z squared equals 4, z greater than or equal to 0. Okay, so I can switch that to spherical coordinates. The radius is 2, so rho is 2. So here's the picture. I factored out the z, x squared plus y squared. This is what you're integrating over. So x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi, but we know the rho is 2. So I got it to two variables being theta and phi. Okay, theta is going from 0 to 2 pi, phi is going from 0 to pi over 2, but it's really long. Okay, so z times x squared plus y squared. Here's z, here's x squared, here's y squared. If you multiply it all out, you get that. So what ends up happening is you have to take r sub theta, r sub phi, then get their cross product. And after a while, I say, okay, it's getting to be too long, so forget about it. Okay, so that's what happened. Then after that, you have to take its magnitude. So it was just getting to be outrageously long. So that's the reason I decided to skip 17 also. Okay. All right, so the only one on this page that you really had to worry about was 15. So let me give you the focus on that. Here we go. Okay. Okay, 23 and 29 are the last ones really to worry about. And I started 25, but that got to be too long. And did I say too long for, let's see, 25. Let's, I did not throw out 25, but it was also very long. Okay. So I didn't say throw out 25. Okay. I'm shortening your assignment even more. So throw out 25 also. After a while, it's kind of hard to count everything. Okay. If you want, just write down 1, 3, 5, 7, 9, all the way up to 31, and then just start crossing these guys out. Okay. 23, it's also long, but I got to do at least one long one, and you got to do at least one long one, right? (23) f of x, y, z is xyi plus yzj plus xzxk. S is the part of the paraboloid. Z equals 4 minus x squared minus y squared. That lies above the square. X going from 0 to 1, y going from 0 to 1. Upward orientation. So upward means positive, as we know. So that's the one Yeah, and we're trying to find the surface integral, double integral of f dot ds. Z is a function of x and y, which means I'm going to do this guy. So double integral of f dot dx, it's the flux of f across S, sometimes it's said. Okay, so across the surface, how much water is getting through, or heat, or electrons, or whatever. So it's a double integral over the region D. Okay, S is the surface. It's a three-dimensional surface object. D is in the XY plane, 0 to 1. So negative P partial of Z with respect to X minus Q partial of Z with respect to Y plus R. Okay, P, Q, and R. So negative P, negative XY times the partial of Z with respect to F, X, negative 2X. Minus Q, so minus YZ times the partial of Z with respect to Y, negative 2Y. Plus R. R is ZX. So Z is 4 minus X squared minus Y squared, there's Z, times X, dA. So here we go. Positive 2x squared y plus 2y squared z. But what's z? 4 minus x squared minus y squared. Plus 4 minus x squared minus y squared x dA. So I got it down to a simple quote unquote double integral with only x and y, which is just a lot of messy algebra. I did some integrating from 0 to 1 for both x and y. Okay. All right, so let's see if I distributed this. 2x squared y plus 8y squared minus 2x squared y squared minus 2y to the fourth, and then distribute here, plus 4x minus x cubed minus xy squared dx dy, or dy dx, either way. Okay, and then I don't think anything combines, so I just have to take it as is. So integrate with respect to x. 2x cubed over 3y, 8xy squared, minus 2x cubed over 3y squared, very long, minus 2xy to the fourth, plus 2x squared, minus x to the fourth over 4, minus x squared over 2y squared. X is going from 0 to 1 dy. Okay, plug in 0, you get 0. Plug in 1 every time you see x. So 2/3 y plus 8y squared. Yes, it's long. Minus 2/3 y squared minus 2y to the fourth. I messed up before, but what's new? Minus y to the fourth plus 2 minus 1/4 minus 1/2 y squared. Okay. Now, I could combine like terms, but I didn't feel like it. I said, I'll just integrate and plug in. If you want to combine like terms, that's fine. I decided to just go with it, especially since I'm plugging in 1. Hopefully that cleans up a lot of stuff anyway. Okay, so 2/3 y squared over 2 plus 8y cubed over 3 minus 2/3 y cubed over 3 minus 2y to the fifth over 5 plus 2y minus 1/4 y minus 1/2 y cubed over 3 from 0 to 1. Plug in 0, you get 0. Plug in 1, that basically makes everything that has a y is 1. So that becomes 1/3 plus 8/3 minus 2/9 minus 2/5 plus 2 minus 1/4 minus 1/6. Okay, so there we go. Common denominator is 180. So I did the common denominator stuff. You can do that as well as I can. 713 over 180. And that actually does match the back of the book, although this would be an example where I really wouldn't trust myself. I highly likely make a mistake on this, but it actually works. And of course, I often say this, if you get the idea correct and you make a calculation error, you're going to get most of the credit. Okay, it's very easy, for this weird thing, very easy to mess up, and very easy for me to mess up also. Okay, 25, just to show you what you're missing, kind of. And then we'll break. f of x, y, z is x plus y plus z squared. S is a sphere with radius 1 centered at the origin. It's the unit sphere. Okay, so x is rho, but rho is 1. So sine phi cosine theta. Y is 1 sine phi sine theta. Z is cosine of phi. Oh yeah, you don't have to pay attention. It's long. Okay, so f now becomes x sine phi cosine theta. Y sine phi sine theta. Z squared cosine squared phi. Remember, for a sphere, in spherical coordinates, theta is going from 0 to 2 pi, phi is going from 0 to pi. But what happens is you take r sub phi and r sub theta. So derivative with respect to phi is that. Derivative with respect to theta is that. Cross product. Okay, it's long. Then you take f dot the cross product. And it comes out to be something super long. Okay, so I decided to forget it. Okay, but notice, just like spherical coordinates, if you have the entire sphere, remember theta goes from 0 to 2 pi, phi only goes from 0 to pi. Okay, so that's it. So you don't really have to look at 25, so I'm not going to show you that. I'll do the focusing job for 23. And then I only have one more problem, but it takes a long time to do that one problem. Okay, and the quiz next time will be something like this last problem that I'm going to show you. Okay. All right, so we'll break as our usual. The only problem I have left is 29. Okay, but it takes a long time to do that one problem, but we'll still finish early, and I'll even sneak in the remaining formulas you need for the last two sections, section 8 and 9. Okay, so I just have one problem, even though it takes a while to do that one problem. And then I'll show you what's happening in 16.8 and 16.9, and then that'll be it. Okay, all right, so let's take our usual break until about 7:10-ish. Okay, so we'll break until 7:10. All right, folks, it's 10 after, so go ahead and pick up where we were. Ben Martinez, I got you for attendance. Okay, so I was going to do just one last problem, but it takes a while to develop it. Then I'll show you the formulas you want to put down for the last two sections, so you at least have it for your next cheat sheet. Okay, so let me try to get started again. Okay, so problem 29. And I'll just go ahead and tell you now, the quiz on Thursday will be just like 29, the one that I'm doing now. So what are we trying to do? Evaluate the surface integral, double integral of S of F dot ds, the flux of F across S, sometimes the language that's used. Okay, so 29, f of xyz is xi plus 2yj plus 3zk. S is a cube with vertices plus or minus 1, plus or minus 1, plus or minus 1, which you've already seen before. Okay, now, that's a cube. They all have very nice normal vectors, which leads me to believe I should use this guy. Integral of f dot ds, double integral of f dot n ds. F dot ds, ds is a vector, capital S. F dot n is a vector. D non-boat S is a surface. Okay, flux of F across S. So here we go. So f of x, y, z, x, 2y, 3z. And here's our cube again. Plus or minus 1, plus or minus 1, plus or minus 1. So front, back, left, right, top, and bottom. Okay, ds for each of the 6 faces is 2 times 2 or 4, right? So the flux of F across a closed surface. So if it's a closed surface, positive is considered out, negative is considered in by convention, right? Show me that picture again. Page 1128. Positive is out, negative is in. So we're going for positive. So a possible example, you've got a room that looks like this, and it might be the flow of heat. So how much heat is flowing off of each surface, the front, the back, the left, the right, the top, or the bottom. Okay, this could be electrons going in and out of the 6 faces. Okay, could be water going in and out, air, gases, or whatever. Okay. All right, so this time, since I have nice normal vectors, double integral of f dot ds, I'll use double integral of f dot n ds. Okay, the front face is x equals 1. What is the unit normal vector out? Okay, it's I, or 1, 0, 0. The back, the unit normal vector is negative I, negative 1, 0, 0. Remember that out is considered positive. Okay, so for the front and back, the front face, it's positive I, but the back face is negative I. I'm just talking about the normal vectors now. Okay, the left face, left one out would be negative j. So the left n is negative j, which is 0, negative 1, 0. How about the right unit normal vector? It's positive j, or 0, 1, 0. So n is j. And then top and bottom, top, positive out is k, 0, 0, 1. Where'd it go? And the bottom, the unit vector out is negative k, or 0, 0, negative 1. Okay, so one more time, just the 6 unit normal vectors outward orientation, right? So the front face, the unit normal out is I, 1, 0, 0. The back is negative I, negative 1, 0, 0. The left outward is negative J, 0, negative 1, 0. The unit normal out for the right side is J, 0, 1, 0. Top, straight up, out, is K, 0, 0, 1. And the unit vector going straight down for the bottom is negative K, 0, 0, negative 1. Okay. All right. So in each case, I need F dot N. So I just take the dot product of F, which is X, 2Y, 3Z, with the normal vector. Okay, so for the front, okay, F dot N, X, 2Y, 3Z dot 1, 0, 0. So it's X times 1 plus nothing is equals X. But what is X at the front? At the front face, X is 1. So my integral is basically going to be 1. Back face, F dot N, X 2Y 3Z dot negative 1, 0, 0 is X times negative 1 is negative X plus 2Y times 0, nothing. 3Z times 0 is nothing, so negative X. Okay, what is negative X? It's negative 1. Remember, the back face has equation X equals negative 1, so it's negative 1. That's also 1. Okay, so F dot N for the front is 1. F dot N for the back is 1. Left, N is 0, negative 1, 0. So F dot N, F doesn't change. It's X 2Y 3Z. So X 2Y 3Z dot 0, negative 1, 0. S component is nothing because that's a 0. Z component is 0 because of 0. So 2Y times negative 1. It's negative 2Y. But what is Y for the left surface? Y was negative 1. So negative 2 times negative 1, 2. So F dot N is 2. Right face, the normal vector is J, 0, 1, 0. You see, this is not really too bad. It's just long. So F dot N, X 2Y 3Z dot 0, 1, 0. X times 0 is nothing. 3Z times 0 is nothing. 2Y times 1 is 2Y. But the right face, what is Y? Y is equal to 1. So 2 times 1 is 2. So F dot N for the right face is also 2. And finally, top and bottom. Top, unit normal, 1 unit straight up, 0, 0, 1. So F dot N, X 2Y 3Z dot 0, 0, 1. X times 0 is nothing, plus 2Y times 0 is nothing, plus 3Z times 1 is 3Z. But for the top face, Z is equal to 1. So I plug in 1, 3 times 1, 3. So F dot N for the top is 3. And finally, the bottom. The unit normal outward is negative K, 0, 0, negative 1. So F dot N, X 2Y 3Z, that's my F. That was the given F. I keep that. That never changes. What does change is the unit normal vector, right? So if I'm on the bottom surface, outward unit normal is negative K. So X 2Y 3Z dot 0, 0, negative 1. X times 0 is 0, plus 2Y times 0 is 0, plus 3Z times negative 1 is negative 3Z. But for the bottom face, Z is negative 1. Negative 3 times negative 1, 3. All right, so F dot DS, F dot N DS. Each of the 6 DS's, non-bode S, is 4. They're all 2 by 2. Okay. So the flux of F across S, F dot DS, is 4 times 1 for the front, plus 1 for the back, plus 2 for the left, plus 2 for the right, plus 3 for the top, plus 3 for the bottom. Total is 48. So there we go. So that's finally the answer. So I hope you see it's not really that hard. It's just long and tedious. And the quiz I'm going to give you on Thursday is very much similar to this. Okay, so I'm done with this. Let me just show it to you. But the idea is this could be thought of as a loss of heat. So if this is a loss of heat, we're losing 4 units across the front, 4 units across the back, and 8 units on the left and right, and 4 times 3 are 12 units across the top and bottom for a net total of 48 units. Positive, meaning going outward of the closed surface. Okay, so there we go. Right, so you can see it's long, tedious, but they're very nice normal vectors, right? I, negative I, front and back. Negative J, positive J, left and right. And then K and negative K, top and bottom. Okay. All right, and I'm done with today's work, folks. I'm just going to show you what's up next, and then if there are any questions, you can ask them. Let me check the chat. Nothing new in the chat yet. So if anybody has any questions they want to ask, you can get ready to either unmute yourself or put in the chat. But what do we have left? So I'm finished with what I was going to do tonight. So next time, 16.8 and a quiz, just like the problem 29 that I just did. Okay. Then Tuesday, 16.9. Then you have the entire class period on the 13th for the test, review for the final, and then you have the entire class period for the final, and then we're done. 16.8, what do you need? Something called Stokes Theorem, page 1134. Stokes Theorem. Okay. So this is one you want to put down on your cheat sheet. It's the higher dimensional version of Green's theorem, where you have a choice. You can either integrate across a curve or a surface. Okay, so integral along a curve of f dot dr is a double integral along the surface of curl f dot ds with positive orientation each way. Okay, so let me show you. There's a little picture here. Okay, so you have a space curve, CC. Okay, and they show you a little stick figure here. This is considered positive orientation. So this stick figure is walking along the curve. This is considered positive because it's in a counterclockwise orientation, right? If you're going in a clockwise orientation, that's considered negative. Okay, but it looks like the stick figure is walking counterclockwise. Remember in Green's theorem in the plane, same thing, positive was counterclockwise, but that's only 2D. So Stokes' theorem is a 3-dimensional version, okay, where you're walking along a space curve and you have some surface above it or below it. And positive for this would be up. As you can see, the unit normals are up like that. So you have a choice. You can either integrate along the curve, f dot dr, okay, work, can be considered work, or the double integral along the surface of curl f dot ds. Okay. Once again, it could get really long. So I restricted it to just problems that I thought were quote unquote reasonable. Not too many. 1 through 7 odd, 13 to 17 odd. Okay, so it doesn't sound like that many problems actually. So this is the higher dimensional version of Green's theorem. Okay, you can choose to either integrate along the curve or along the surface. Now, among other things, that means you can imagine more than 2 surfaces that have the same boundary curve. So imagine if you have this thing coming way up or whatever, or taking the bottom and holding the boundary curve, but blowing that up more, okay, you get the same answer because you have the same boundary curve, right? The text goes over a little bit of a sort of a proof of a special case. You can look at it or not, okay? But that does mean I can even answer question number 1 right away because there's really nothing to it. So let's see, I can mark off 16.7 now. So 16.8, I'm going to do number 1. There's really no work to it. Okay, let's take a look at this again. You can either integrate along the curve or along the surface. You have a curve and a boundary surface. Now look at number 1. A hemisphere H and a portion of a paraboloid are shown. Suppose BOD F is a vector field on R3 whose components have continuous partial derivatives. Explain why the double integral along the hemisphere of curl F dot ds is the same as double integral along the paraboloid of curl F dot ds are the same. They have the same boundary curve. They have the same boundary curve. That means for both figures, the left side is the same. Integral of C F dot dr. So that means it doesn't matter what the right side is, as long as you have the same boundary curve, you're going to get the same result. If you have nice functions, so to speak, they define it, of course, with continuous partial derivatives on an open region. Okay, and if you stop and think about it, it actually makes sense. Imagine you have a nozzle here, a nozzle, and you fill it with water, and this is a boundary, but water can pass through it. Okay, so if I shoot water across here, and if I shoot water across here, well, the same amount of water is going to come through, whether it's like this or like this. Okay, it doesn't matter what the surface here. I can make this go up 1,000 miles and come back down. Eventually, if there's nothing else going on, the same amount of water is going to flow through because you're really just looking at the boundary, right? So it doesn't matter if the boundary is like this, or I could even just have the regular circle. If I just have the circle in the plane, the same amount of water is going to go through there as it's going to come through here, as it's going to come through here, because you've got the same boundary curve, right? I said water, it could be heat, it can be electrons or whatever. Okay, so that's what we're up against for Stokes theorem. Finally, 16.9. So your last formula for the course, you'll be happy to know. The divergence theorem, page 1141. So put this one on your cheat sheet. Double integral around a surface of f dot ds is a triple integral over the region E of div f dv. Okay. So E is a simple solid region, S be the boundary surface. Okay, so it's a closed surface, sort of like the one I just did with that cube. Okay. So double integral of f dot ds is going to be the same as a triple integral of E of div f dv. Now, ordinarily, you might think the triple integral is going to be harder, but usually the triple integral is easier because let's take the problem we just did that had the 6 surfaces, right? We had to do 6 double integrals. So which would you rather do? 6 double integrals or 1 triple integral? No, 1 triple, right? As opposed to, so the left-hand side, that's kind of like, okay, you got to do the front, the back, left, right, top, and bottom. Or you can just do 1 triple integral. So yeah, triple integrals, they can get long, but at least you're just doing 1 as opposed to doing 6 double integrals. So that's called the divergence theorem. So we're doing some problems involving that. And to wind up the course, you don't have to write this down if you don't want to, but they give a nice summary of all the fundamental theorem of calculus forms that you had, Calc 1, 2, and 3. So Calc 1 and 2, integral from A to B of capital F prime of X dx, f of B minus f of A. Right? You just have to check the endpoints. It's basically you're just looking at the boundary. Okay, fundamental theorem for line integrals. If you have a conservative vector field, integral along C of del f dot dr, f of r of B minus f of r of A. There's the picture. That picture is the 3-dimensional equivalent of the first one. First one was Calc 1 and Calc 2, right? Now in Calc 3, You just move it to 2 or 3 dimensions. Green's theorem in the plane, you saw that. You have a choice. You can either integrate along the curve, positive orientation, notice the arrow, positive counterclockwise, or the region. Stokes theorem makes it higher dimensional. So imagine taking Green's theorem and then moving it into space. So you have a space curve and a space surface. Okay. Even though it's a space situation, you can still talk about positive orientation, right? So C, positive. And N, positive, is considered up. And then the divergence theorem, you can choose either integrate along all the surfaces with all the different normal vectors. See, positive is out, right? So normal vector up, down, left, right. They didn't draw the front and back, but it's there. Or you can do the triple integral of the region E that's there. Okay, so Thursday, we'll be doing 16.8. This is what we're doing. I already did number 1, which is not really much work. And then I'll give you a quiz just like problem 29. Tuesday, do the divergence theorem, and then let you ask questions in preparation for the test. Okay, and then that'll be it. And then we're ready for the last regular test. Okay, so that's where we're at. How long is the final exam? Well, you get the entire 2.5 or 2 hours and what, 2 hours and 15 minutes. No, it probably won't be 10 questions, maybe 15 or 20. Okay, so if I give 3 questions per test, that would be 3 times 5 is 15. If I give 4 each, then maybe 20, but I'm leaning toward 15 because we know some of the problems can get really long. Okay, so likely 15 good questions, 3 from each of the previous exams for the final exam. Okay. All right, I'm done, folks. Anybody want to ask a question? You can either unmute yourself or put it in the chat. Otherwise, that's it. So next time, do section 8, and then we have a quiz. That'll be our last quiz. Then Tuesday, section 9, and again, Tuesday, you can come up with any questions from anything here. So hang in there a little longer. We're almost done, folks. Okay, any other questions, please? Wait just a moment. In case somebody's typing. All right, I don't see or hear anything, so we're going to call it a night. All right, so that's it, folks. Have a good night, and we'll see everybody next time. Okay, bye, everybody. Night.
Thank you very much. Have a good night.
Have a good night.
Good night.
Thank you.
Thank you. Good night.
Thank you. Good night.